Okay, so our next speaker will be Richie talking about the Eden simulation. So go ahead.
Does this work? Yeah? I'll just, yeah. No, I mean, it's just not facing the right direction. All right, so hello everyone, good morning. I'm Richie from Stanford. I primarily work with Teresa Wexler. I'm very happy to be back this year. Shifting gears a little bit, I won't be talking that much about feedback. This work is mainly motivated by star formation studies of dwarf galaxies in the Saga survey, and this is really an n-body simulation, so no fancy star formation or feedback or anything, but I think it really fits nicely into the topic of this session as we sort of isolate the effect of star formation and feedback and really look at the gravitational effects of the galactic disk on subhalo populations and revisiting this topic, which is very important for interpreting Milky Way satellites. So I think I want to start the background about this work, which is observationally over the past decade or so, there has been a concerted effort in the field trying to build up a very large statistical sample of satellites around a diverse set of Milky Way mass hosts. So probably before 2010s, where the most of the satellite discovery space below, say, the LMC mass was in the local group, right, in the Milky Way and M31, and these are the closest systems where you could go very faint in terms of satellite luminosity, and it's well studied. And we have about 100 of these discovered in the local group. But to really understand how satellite properties and how the diverse host properties affect the satellite populations, we really want to build a large statistical sample of different hosts. And there comes the ELF survey, which is roughly within the local volume of 20 megaparsecs, and it's a photometric survey looking at about 7 satellites down to roughly 10 to 6.5 per system. And we have the Saga survey, which is a spectroscopic survey over 100 hosts and almost 400 satellites down to 7.5 in each host, and you're looking on average of 4 to 5 satellites per system. And this big statistical sample is really helping us gain a better understanding of the cosmological context of the Milky Way and M31 satellite systems in the entire universe compared to their similar mass host siblings. And in terms of the satellite luminosity functions that we're looking at, M31 and the Milky Way really sits nicely in the 101 different hosts in Saga, and this is the NSAT as a function of stellar mass. And we've been trying to model the star formation histories of the satellite systems in a cosmological context using the universe machine empirical modeling framework by ROOTC 2019, as many people know. And we've upgraded this framework and extended all the way down to 7.5. Basically, this model forward predicts the star formation rates of galaxies in a cosmological dark matter only simulation based on halo mass and accretion history. And we're able to reproduce not only the mass functions, but also the galaxy quenching properties of low mass galaxies as a function of their mass and environment. So the green here is for satellites, and the blue is for the field, down to roughly 10 to the 7. So this was my talk last year here, and if you're interested, please check out the online YouTube video. I'm not going to talk a lot about this in this talk this year, but this is really where Eden was motivated, and I got this question here last year, and also at many other conferences, that every time when I finish talking about the amazing work that we've done with these dark matter only simulations and empirically connecting them to observations, is how do you account for baryonic effects? And the answer is, in that work we didn't. And this could be a very significant effect on the subhalo populations that you're basing your galaxy halo connection on. and comparing to observations. And there's just enhanced tidal stripping from the baryonic content of the host galaxy itself. So back in 2017, Garrison Kimmel et al. In the FIRE team resimulated 2 of their FIRE 2 simulations with embedded disk potentials. So here on the left, you're looking at the dark matter only component, and in the middle, this is the full hydro run. And on the right is, instead of doing the full hydro run, you replace the baryons with an analytic potential that follows the disk growth in the hydrodynamic simulation, but everything is dark matter only. You're just adding another potential to it. And actually, this is just a pure mass effect, and without any star formation or feedback, it can alone create a significant suppression of subhalo abundances in the central regions, as you see here, compared to the dark matter only case. And in 2019, Tyler Kelly et al. Expanded from 2 halos to 12 halos in the Fat Elvis suite, found a very similar thing. If you just added an analytic disk potential, you can get pretty similar results for the subhalo population in a dark matter only simulation. So this is a nice and fast way to embed disk potentials into dark matter only to approximate baryonic effects. And it basically also has the neatness of isolating gravitational effects, pure gravitational effects from your specific choice of treatment of feedback physics. So that brings us to Eden, which is really nicely summarized in this plot. And if we think about all the 12 or 14 embedded disk simulations that's marked out as orange up here, it actually is all tailored to the Milky Way itself, right? So all the red error bars are recent measurements on the Milky Way stellar mass and halo mass. M31 is up here in magenta. It's really, if you compare it to the shaded regions in the background, that's the Beruzzi 2019 empirical stellar mass halo mass relation for around L-star galaxies and around 10 to the 12 halos. Milky Way and M31 really has a large disk compared to their siblings. And there's a huge amount of parameter space down here where similar L-star galaxies occupy 10 to the 12 halo, but there just has been no similar simulations of embedded disks for this mass range. So we really want to enlarge the statistical sample of embedded disk simulations, and here we're based on the Symphony simulation compilation of 45 Milky Way mass zoom-ins. We want to better sample the full range of host stellar masses that occupy this range, and also we want to sample the diverse disk formation histories, right? So at similar masses, you also have different assembly histories, and we want to anchor that on halo assembly. And of course, the main goal is to establish a cosmological context for Milky Way and M31 satellite systems at the end of the day. So the way we did this is to really let the disk grow in our 45 Milky Way mass hosts according to whatever universe machine predicts, because it automatically ties the star formation histories of the disk to the halo accretion histories. So we embed them since redshift 3, that's the vertical line here, and we let them grow, and that are the gray bands and the individual thin lines here. Now compared to some of the latest constraints on the Milky Way's disk assembly, and we've heard some talks about this yesterday, the Milky Way can really form the disk really early on. And so most of the Eden hosts that we have grow later and end up in lower end star than the Milky Way, which is not surprising. And so to really curate a sample for Milky Way-like and M31-like systems, we resimulated 9 of our hosts with 2.5 times higher disk mass, and their average is the dashed gray curve we see here, which fits nicely with the Milky Way constraints. So this high mass subsample, I'll just call it like times 2.5 following on, and comparing the Eden hosts here in gray to the previous simulations I mentioned, the 2 fire hosts in orange, and also the Fat Elvis, 12 of the Fat Elvis hosts in the dotted cyan, you can see that the default Eden host, of course, is lower mass and forms a bit later on average, and these look like the Milky Way. and the high mass subsample we curated is very similar to these previous works. And apart from this, we also updated our halo finder, which Phil would talk about on Friday. And we have the Symphony particle tracking halo finder to enable a more robust subhalo tracking than Rockstar. So the key point here is that when we look at the variations in the M star over M vir for our Eden hosts, if we look at the lowest, say, quartile of the disk to halo mass ratio that we embed in, you don't see a huge difference in the subhalo populations in the disk runs versus the DMO. But once you add a very large disk in, you can immediately see that the inner regions especially changes a lot, and you see less substructures, higher central densities, and rounder halo shapes. And if you focus on, say, the inner 100 kpc, then that's where most of the action happens. So there are two competing effects. You have adiabatic contraction due to added disk. You just draw more stuff in towards the inner regions. But also because of the disk, you have enhanced tidal stripping, and you lose your substructures. To really quantify these two effects, it's really nicely summarized in this plot. You count the subhalos, say within 100 kpc in the disk run versus the DMO run, and see their ratios, right? And the blue crosses is what you would expect just from pure adiabatic contraction. You get more stuff as you put a larger disk in. But in reality, when you look at the Eden host, it actually decreases in this ratio with increasing stellar mass of the disk itself. So disk disruption takes over adiabatic contraction at the very large end. The red band is the Milky Way. The blue band, or the magenta band, is the M31. And this is where you really have to start worrying about losing a lot of subhalos, more than 50% of them, in the inner regions. So probably for most of Saga and also L survey, where you're about 2% in terms of the host disk to halo masses, you're pretty much fine. We also look at other things like the subhalo mass function, the distribution of pericenters, and also infall time. They're pretty consistent with previous works. And the idea is that you preferentially lose subhalos that fall in early on and also encounter smaller pericenters. So to finally, as the last part, to sort of advertise and put this into context, we have another suite that's been put out in the past 2 months, led by Devanshi Buk, who was an undergrad in our group. And this is a set of 20 realistic Milky Way-like hosts with very realistic LMC and guidance Zeldas mergers curated. And you can see here on the right the density plots where you have the LMC in all of them. And we're in the effort of running embedded disk simulations in all of them. And I think this will be a great platform for a lot of Milky Way-related sciences in the next 5 years. For satellites, stellar halos, stellar streams. Phil's also going to talk about this on Friday. And I'll just leave my summary here, which is probably this is the most important take-home, that disk to halo mass ratio, as we find, is a very important factor in deciding the subhalo abundances. And for our Milky Way and M31, they're amongst the most efficient, say, disruptors in the universe due to their large stellar disk. So with that, thank you for your attention.
Any questions?
Great talk. So I was wondering if you also looked at the quiescent fraction of the satellites in this model.
Not yet.
So okay.
Not yet.
Yeah, this is great. I'm going to ask you something that you didn't talk about, but we've gone back and forth a little bit. So there's this question of what happens in 10 to the 13 solar mass halos, because those are the lens hosts, and we're interested maybe in how much really low mass substructures there for lensing. And the naive expectation from this, which I think is probably mostly right, is that destruction probably not going to matter that much because those things have fairly low M star to M halo ratios. But one potential caveat from that is, 10 to the 13 solar mass halos do have a lot of 10 to the 12 solar mass mergers. when those mergers happen, the M star to M halo ratio is lower. So maybe it doesn't matter, but there's sort of some kind of the fact that you only have one embedded potential and you don't have embedded potentials in the things that are merging in principle could matter. I just wonder if you could comment on that. Like, how confident should we be as we go up the mass hierarchy that we can ignore this effect, I guess is the question.
I think that's a great point, and we want to definitely explore that idea. My one-shot take on that is probably it depends on the infall time of that progenitor, right? So if it had enough time or enough pericenters for its like sub-halos to get disrupted by its baryonic potential, then yes, it's going to matter. But if it's a recent merger, or sorry, if it's high redshift and happened at redshift 1, if you look at the star formation histories we had, the disk wasn't that prominent. So an effect that I did not mention is that it's also correlated with the formation time of the disk itself. And in the Milky Way case, right, a larger disk is also early forming, so it had longer to impact its subhalo populations. So I think the assembly part is also something we need to look into.
All right, let's thank Richie once more.